Hello friends, welcome to the course Atoms and Molecules for MSc Physics as per the revised syllabus of Savitribai Phule Pune University CBCS 2019 pattern. So we are studying our second module, molecules. So in the today's lecture, we will study the vibrational spectra of diatomic molecules. So let us study the variation of potential energy with respect to the interatomic separation. When the two atoms are at infinitely long separation between them, then the potential energy is somewhat equal to 0. When the two atoms starts approaching each other, then the potential energy starts decreasing. In that case, the attraction between the two atoms is dominant over the repulsion term. The potential energy starts decreasing, and at a point we get a minimum in the potential energy. We call it V0. At this point, the separation between the two atoms, we call it equilibrium separation. Further, if it decreases the separation between the two atoms, then the potential energy again rises, right? So that means the repulsive term dominant over the attractive term. At the minimum value of potential energy, the attraction term and repulsion term, they balance each other, and therefore we get a minimum in the potential energy. So let us see the typical potential energy curve for the diatomic molecule. When the two atoms are at infinitely long separation between them, then potential energy is equal to 0, and the potential energy starts decreasing when the two atoms they approach each other, and the potential energy is minimum at a point called as equilibrium separation, where the separation between two atoms is equal to R equilibrium. And further, if we decrease the separation between the two atoms, then the potential energy is again rises. That means the potential energy has a parabolic kind of shape in this region, right? So if the separation between two atoms increases, then the bond between two atoms, it will break, right? So within this region, we can say the bond is formed between the two atoms, and when the two atoms they vibrate about their mean position, right? So due to the vibration, there will be variation in the potential energy. So the diatomic molecule behaves like a simple harmonic oscillator within this region. So we apply the harmonic oscillator approximation to this region. So within this region, we say the curve is parabolic, right? So within this region, the curve is parabolic. That means our diatomic molecule follows the harmonic oscillation. This is the diatomic molecule. So R equilibrium is the nuclear separation between the two atoms. So this diatomic molecule is continuously vibrating about in mean position. So real molecules may be harmonic or unharmonic. So that means if the energy provided is large enough, then the bond between the two atoms it may break, right? And therefore that molecule is unharmonic, and therefore that shows the typical the curve called as Morse curve, right? So that curve we have already seen. So let us study the vibrational spectra of diatomic molecule. So when the diatomic molecule vibrates, there will be change in the vibrational energy levels of the diatomic molecule. When the external electromagnetic radiation interacts with these energy levels, the diatomic molecules goes from one energy level to another energy levels, and therefore in this process the energy will be absorbed or emitted, right? So that results in the spectrum called as vibrational spectrum of the diatomic molecule. So here we are considering the pure vibrational spectra of a diatomic molecule. So the vibrating diatomic molecule may be considered to be equivalent to the two masses connected by a spring. If M1 and M2 are the masses of the two atoms of the molecule, then the reduced mass of the molecule is mu is equal to M1 M2 upon M1 plus M2, where mu is called the reduced mass. The vibrations of the spring may be unharmonic. We approximate the vibrating diatomic molecule undergoes small vibrations so that it follows the simple harmonic oscillations. So, within the parabolic approximation, we consider our diatomic molecule follows the simple harmonic oscillations, and therefore, let us consider the spring obeys Hooke's law. The restoring force is directly proportional to the displacement from mean position, and it is given by F is equal to minus K into R minus R equilibrium, where K is the force constant and R is the interatomic distance. In this case, the energy curve is parabolic and has the form E is equal to 1/2 K into R minus R equilibrium bracket square. The classical frequency of oscillations of the diatomic molecule is given by omega oscillations is equal to 1/2 pi square root of K upon mu, which is in Hertz. So, by dividing this frequency by c, velocity of light, which is expressed in centimeter per second, we get omega bar oscillations is equal to 1/2 pi c square root of K upon mu, which is in per centimeter unit. However, the vibrational energies of the molecule are quantized, and the allowed vibrational energies for simple harmonic oscillator are given by solving the SHO problem quantum mechanically. Thus, E nu is equal to nu plus 1/2 h omega oscillations, which is in joules, where h is Planck's constant and nu called the vibrational quantum number, which takes the values as nu is equal to 0, 1, 2, 3 up to infinity. The lowest energy state is for nu is equal to 0 and called as the 0 point energy, and it is given by E0 is equal to 1/2 h omega oscillations, which is in joules, where omega oscillations in expressed in Hertz, or we can write in per centimeter units. So, we can write E0 which is equal to 1/2 omega bar oscillations when expressed in terms of per centimeter or wave number units, right. So, we can see from this equation that the 0 point energy of the harmonic oscillator is not 0. That means, it has some energy, and that energy is called as 0 point energy. So, the next energies are given by E1 is equal to 3/2 h omega oscillations, E2 is equal to 5/2 h omega oscillations, E3 is equal to 7/2 h omega oscillations, and so on, which is in joules, right. Or when we express in terms of per centimeter, we replace this h omega oscillations by omega bar, right. Thus, the successive energy levels are equally spaced and are separated by h omega oscillations or omega oscillations bar, right. So, these vibrational energy levels are shown in figure for different quantum numbers, nu is equal to 0, 1, 2, 3, right. So, we get different values of the energies corresponding to the quantum numbers, right. So, E nu is given by nu plus 1/2 omega bar oscillations, where nu takes values from 0, 1, 2, 3 up to infinity, and therefore, for nu is equal to 0, E0 is equal to 0 plus half omega bar oscillations, which is equal to 1/2 omega bar oscillations. That means, the energy of the harmonic oscillator is not 0, but it has some energy, right. So, for nu is equal to 0, we have the energy, and that energy level is equal to 1/2 omega bar oscillation, right. For nu is equal to 1, we get E1 is equal to 3/2 omega bar oscillations. For nu is equal to 2, we get E2 is equal to 5/2 omega bar oscillations, and for nu is equal to 3, we get E3 is equal to 7/2 omega bar oscillations, right. So, these are the vibrational energy levels of the diatomic molecule. Now, when the transition from higher energy state to lower energy states takes place, the energy is emitted in the form of radiation. But when a transition from the lower state to the higher state takes place, then in that case the energy will be absorbed. So, there are some selection rules for the transition between the vibrational energy levels, and which is given by delta nu is equal to plus or minus 1. That means, during the transition, the quantum number nu must change by plus or minus 1 only, right. All the other transitions are not allowed. Therefore, the transition between any two successive energy levels will give energy is equal to h omega oscillations or omega bar oscillations, because each energy levels they are separated by omega bar oscillations. So, let us see this here. So, we know the selection rules. So, from selection rules we can write, so the transition from E nu plus 1 to E nu, the transition we can write as nu plus 1 plus half omega bar oscillations minus nu plus half omega bar oscillations, and therefore we get for that transition which is equal to omega bar oscillations, right. So that means the wave number for the spectral lines absorbed or emitted are given by nu bar that is emitted, which is equal to E, which is equal to omega bar oscillations. That means the oscillation frequency expressed in per centimeter unit, that is equal to the wave number that is emitted or absorbed, right. So all the successive transitions give the same frequency of emission or absorption. That means we get the same wave number for all the transitions, and therefore all the transitions we get it is omega bar oscillations. For large oscillations, the Hooke's law is not obeyed exactly by real molecules, and the bond may not be elastic, right. So up to now we have considered the harmonic oscillator, right. So our diatomic molecule within the parabolic approximation, we consider it follows the harmonic oscillations. But for large oscillations, the Hooke's law is not obeyed exactly by real molecules, and the bond may not be elastic, and therefore for large molecular vibrations they are unharmonic, right. As a result, the spacing between the adjacent energy levels of high nu is less than the spacing between the adjacent levels of low nu, right. So let us see the unharmonic oscillator. So real molecules do not obey exactly the laws of simple harmonic motion. So if the bond between the atom is stressed, for instance, there comes a point at which it will break, and thus the molecule dissociate into atoms. A purely empirical expression which fits the curve to a good approximation was derived by PM Morse, and it is called the Morse function. So Morse function is given by E is equal to d equilibrium into 1 minus exponential of A into R equilibrium minus R, so whole bracket raised to 2, right, where A is a constant for a particular molecule and d equilibrium is the dissociation energy. So the dissociation energy we can see here, right. So this is the Morse curve, right. So this kind of curve is called as Morse curve, and here we consider the parabolic approximation. So we say that within the parabolic approximation our diatomic molecule behaves like an simple harmonic oscillator, right. But real molecules, they are not simple harmonic, but they are unharmonic, and therefore for the real molecules we get this kind of curve, right. When the separation between the two atoms increases, then the bond between the two atoms breaks, right. So at a particular point the bond between the two atoms breaks, and that particular energy we call it the dissociation energy. So that dissociation energy is shown here. So it is d equilibrium. So for a particular energy level, vibrational energy level, so this is an electronic energy level. So for a particular electronic energy level we have the different vibrational energy levels, we will see in the upcoming lectures. So the corresponding dissociation energy is shown here. So the allowed vibrational energy levels are given by E nu is equal to nu plus half omega E bar minus nu plus half square omega E bar into Xc, right. So this particular expression is for the harmonic oscillator, and this expression is for, we have added the term due to the unharmonic term, right. So this term is unharmonic term which is added to the energy, where omega E bar is an equilibrium oscillation frequency of the unharmonic system, and Xc is the corresponding unharmonicity constant, which for a bond stretching vibrations is always small and positive, so that the vibrational energy levels crowd more closely with increasing energy. So the omega E bar is the equilibrium oscillation frequency of the unharmonic system, right. So we say that within the parabolic approximation omega bar oscillations is equal to omega bar E. So the oscillation frequency is given by omega bar oscillation, which is equal to omega E bar into 1 minus Xc into nu plus half, right. So for the ground state nu is equal to 0, and therefore we get omega 0 bar is equal to omega E bar into 1 minus half Xc, which is in per centimeter, and corresponding energy is E0 is equal to 1 half omega E bar 1 minus 1 half Xc, which is also in per centimeter, and the 0 energy differs slightly from that of harmonic oscillator. So this is the the 0 point energy for unharmonic oscillator, which differs slightly from that of the harmonic oscillator, right. So, within the parabolic approximation, if we say this Xc is equal to 0, in that case we get the omega bar oscillation is equal to omega bar E. So, this is a typical Morse curve for the unharmonic oscillator, right. So, we have the dissociation energy or D equilibrium. So, this dissociation energy is expressed here, and this is the D0, that means the dissociation energy from the 0 point energy, right. So, from nu is equal to 0, we get the dissociation energy from the ground state or from the 0 point energy, right. So, vibrational ground state is nu is equal to 0. So, the selection rules are delta nu is equal to plus or minus 1, plus or minus 2, plus or minus 3 up to infinity, right. So, they are the same as for the harmonic oscillator with additional possibility for larger jumps, right. In the case of harmonic oscillator, only delta nu was only plus or minus 1, that means only the nearest transitions were allowed, right. From 0 to 1, 1 to 2, 2 to 3, all these transitions were allowed, but now there is additional possibility of larger jumps, right. So, that means from nu is equal to 0 to nu equal to 2 transition can take place, from nu is equal to 0 to nu is equal to 3 transition can also takes place, right. So, with the increase in the nu value, the difference between the two levels, the probability of transitions also go on decreasing, and therefore, we consider only the nearest possible transitions, that is up to delta nu is equal to plus or minus 3 only. So, let us consider the 3 transitions. So, first transition is from nu is equal to 0 to nu is equal to 1, right. So, this transition, for this transition delta nu is equal to plus 1. So, with this transition will appear with considerable intensity, and it is will be equal to delta E is equal to omega E bar into 1 minus 2 Xc. So, corresponding transition is shown here, and we get the particular wave number at omega E bar, right. So, this transition is called as fundamental absorption, right. So, this transition corresponding to nu is equal to 0 to nu is equal to 1 is called as fundamental absorption, and corresponding wave number is omega E bar. For the transition, for the next transition nu is equal to 0 to nu is equal to 2, for that case delta nu is changed by plus 2, and this transition will appear with small intensity, and therefore, delta E for that case is equal to 2 into omega E bar into 1 minus 3 Xc, right. So, that transition will appear here. So, it is 2 omega E bar, right, and it is called as first overtone, right. So, the first overtone appears with small intensity. The third transition is from nu is equal to 0 to nu is equal to 3. For that case, delta nu is equal to plus 3. So, this transition will appear with negligible intensity, and therefore, delta E for that case is equal to 3 into omega E bar into 1 minus 4 Xc, which is in per centimeter, right. So, this transition appears with negligible intensity, and it is called as second overtone, right. So, this particular transition from nu is equal to 0 to nu is equal to 3 is called as second overtone, right. So, in summary, we have learned the vibrational energy levels of a diatomic molecule, and we have considered the harmonic oscillation approximation, and we have also considered the real unharmonic oscillator, right. So, in the next lecture, we will study the vibrational core structure. Thank you.